Ladies and gentlemen, we have but 2 new lessons left in this class.
Wow.
This is your second to last new lesson. So we're going to talk a little today about work, and then we'll spend a couple days talking about work, and then you'll take a chapter 7 test, and then we have one little section left in chapter 8, and we're done. And then the fun starts. Woohoo! So today's a little bit of physics. Just a little, hold on, before you lose it. A little bit of physics, but then we'll change from physics into math, because math is much more important than that comes to physics. Okay. So I'm sure you've all had physics, yes? What is work?
Energy needed to move.
What you do.
Work has to do with force and distance. So I don't know what you did in physics, nor do I care, but we're going to talk about 2 different scenarios. One where you have a constant force, and for us, most of our calculations, force will be weight. Okay. So for instance, if I come over here and I pick up Ryan, and I lift him 6 feet in the air, that's an easy calculation. What do you weigh, like 110 pounds? Oh, it's close. Okay, so I take 180 pounds, lift him 6 feet in the air, it's 180 times 6, done. Right? That doesn't require calculus. It doesn't really require anything except simple multiplication. But that is something involving a constant force. Now, if you do the same thing but something changes, the weight changes in the problem, now all of a sudden you get what's called a variable force. Okay, so I start picking up Ryan and his leg falls off. And I lift him a little higher and his arm falls off. And then I lift him a little bit. So the weight there is changing. And when it changes, now we need to start incorporating some calculus. Okay. And then you should also be able to juggle 3 balls. How many people can juggle? Nobody? 2? Anybody? Yeah.
I can juggle.
You can do 3?
I can do 3, yeah.
Nice job. You can demonstrate later. Okay. Can you do chainsaws?
Oh, no. That more big.
Maybe in a circus. Or you'd be on America's Got Talent. Or you'd be in the hospital. Okay, so we pretty much covered this already, lifting Ryan up. However, just to make it official, force times distance. Force is weight for most of the problems that we talk about. Okay. There's a whole bunch of different other forces. Most of these we're never going to see, except gravitational. That's a big one for us. We're not really going to spin things in circles. We're not going to hook up motors. We are going to deal with gravity, and we don't do anything involving Luke and Ray. Let's imagine Ryan weighed 50 pounds, and I lifted him 4 feet. I would do 200, yeah, look at those cool units, foot-pounds, or pounds-foot, and either one is correct. I think it would be pound-foots, though, pound-feet. Let's just go with foot-pounds. Okay. That's not very exciting, and like I said, does not require calculus. So on the worksheet that I gave you, you will notice that there are 4 problems on there. We're going to take a sidebar for a second and talk a little bit about this guy named Robert Hooke. He spent his entire career studying 2 things, physics and springs. Okay, he probably did more, I'm embellishing. So we're going to talk about how springs work, and then we're going to transition from that into some more exciting problems. But before we do that, let's go back to this slide. How is what we did with Ryan different from what we're going to do with springs and the beam in the problem and the leaky bucket? Because the weight is changing over time. And so we start to incorporate calculus there by calculating the amount of work required to change a small thing, and then integrating it to add up all those little chunks of work. It's the same thing we did when we calculated volumes and areas. We use one little volume, and then we add up all the possible volumes. But again, springs are a little weird. The only reason I'm covering springs is because I found this fun picture of Robert Hooke. I mean, it's dreamy, isn't he? That's the Bachelor material right there.
Yeah.
Yeah. Anyways, and is that another picture of Hooke? Oh, I like that one better. He's got fancy curly hair. He looks like Annie. The sun will come up. Anyways, so if you think about a spring, if you pick up a spring and hold it, it will stretch a little bit, for the most part. I mean, ignoring like a big car spring or a garage door spring. Think of a spring like a slinky. You pick up a slinky and it stretches down a little bit, right? But then it stops stretching and it hits that like kind of just hanging position. That's what's called the natural length of a spring. And all springs have different natural lengths. Some springs, if they're very rigid, like the spring on your garage door, won't change at all because the spring is very rigid. Other springs, like slinkies, stretch quite a bit. That's determined by the spring's natural length and what's called the spring constant. So Robert Hooke plays with a bunch of springs and comes up with something that he names after himself called Hooke's Law. What a creative name. The force for that spring is determined by the spring constant times the distance that it stretches. So every spring has a spring constant. We're going to use that to calculate the force that we need for our work problems. Okay? So, here's some springs. What we know about the springs are the following. The spring has a natural length of 8 inches. You pick it up and you let it just hang there, it's going to stretch to 8 inches. If you hook a 12-pound force up to that spring, it's going to stretch a total of 3 more inches, down to 11 inches. So we don't want to think about that as 8 and 11, we want to think about that as 0 and 3. Does that make sense? So the natural or neutral length, like it says up there, is considered 0. And then we can either stretch it or compress it. What we don't know about the spring is the spring constant, so we have to calculate that first. And once we calculate the spring constant, we can answer these 2 questions about work. Okay, so how do we calculate the spring constant? Well, we use that force equation we just had. Okay? Force is equal to K times X, where the force in this case is 12 pounds. X is the distance that it was stretched, which is 3 inches, which leads us to a nice easy spring constant for this one of 4. Any problems there? In every one of these spring problems, they will either give you the spring constant or you'll have to calculate it using Hooke's law, F equals Kx. Now, that doesn't help us answer part A. Part A then requires, well, it does help us, but it's not going to, I'll just stop talking. Let's move on. Okay, so now we want to know how long it, or how much force is required, how much work is required to stretch it from 8 to 13. So we've got to put a little bit more work into it because we're stretching it more than just the 3 inches it stretched previously. We're actually stretching it a total of 5 inches. And that gets us to this. Okay, now where did that come from? 4x is our force. That's Hooke's law, K times x. dx is the distance we're moving that spring, just a little bit, because remember the differentials mean very small distances. And then the integral adds up all those chunks of work from 0 to 5. By the way, how many chunks of work will there be from 0 to 5? Little philosophical question for you there. Let's back up. How big is dx?
Super tiny.
Super tiny. So if dx is super tiny, then how many little increments of work do we have? A lot. Specifically? Infinite, correct. So theoretically, dx is going to go down to 0. As dx goes down to 0, the number of chunks of work we have goes to infinity. But we don't care about any of that because the integral takes that into account. That's an easy integral to solve. and you get an answer of, you get an answer of 50 inch-pounds. Force times distance, weight times distance. What's going to change between problem A and problem B? See again? Right. So in that equation, W equals the integral from 0 to 5 of 4x dx. What's going to change? Good. Instead of 0, it's going to be 2. Doing the calculations here, will the work go up or down? Down, right, because you're moving in a shorter distance. Instead of stretching it 5, you're stretching it only 3. And it does go down, 42 inch-pounds. Okay, so springs with work, springs are kind of outside the normal type of work problem. The last 3 problems you have on that worksheet are more what's considered a traditional work problem. But as I said, occasionally springs pop up, so I wanted to cover it just so you weren't absolutely blown away by it when it did show up. Of course, now that I've covered it, it won't show up. If I didn't cover it, it would have been half the test. All right, so let's talk about this beam. I'm lifting an 800-pound beam up the side of a building. And I'm using a cable. That cable is heavy. It's got to be heavy to support an 800-pound beam. So if the cable gets very heavy, you have to start to take into account the weight of that cable. Okay, so let's say, for instance, you're picking up something on a piece of fishing string, fishing wire. What is it called? Fishing line. Fishing line can be pretty strong. 100-pound test, for instance, will hold up to theoretically 100 pounds. If you stretch that fishing line from 6 feet up to 2 or 3 miles, all of a sudden it's going to snap under its own weight, because you take 3 miles of fishing line and it weighs more than the line itself can bear. And so this problem, we have to take into account the weight of the cable. What doesn't change in the problem? When I lift that beam, what doesn't change? Weight of the beam. It's always 800 pounds. Ryan is always, what'd you say, $110, $120, $180?
Yeah.
Ryan is always 180 pounds, whether he's sitting in his chair or I've lifted him 6 feet off the ground. So that part of the calculation was a constant force. However, what is changing is the weight of the cable, because less cable is out as you pull it in. So you have the picture there. And notice as I start to pull that cable in, the amount of cable left outside that needs to be taken into account decreases. So initially the cable weighs 150 pounds. Let's suppose I pull in 1 foot of cable. How much does it weigh now? Yeah, that wasn't meant to be a difficult question. Let's try that again. Suppose I start the problem with 150 pounds of cable and I pull in 2 feet of cable. How much am I left with? 144. There you go. I knew I'd get you. Okay, and then let's suppose I start with 150 pounds of cable and I pull in X feet. How much will the cable weigh now?
150 minus 3x.
Beautiful. So we make a big jump here, and we get to that. Every foot of cable weighs 3 pounds, and therefore, the weight at any point in the scenario would be given by that expression. The 800 never changes. The weight of the cable decreases with the more you pull in. So I'm going to move that weight a very tiny amount, which I'll call dx. And then I have to add up all those little dx's from 0 to 20, which gets me to that equation. Now, a common mistake with a problem like this is people want to incorporate the 20 into the integrand. You know what I mean by integrand, right? Does everybody understand what that means? Because that's important. The integrand is the thing you're taking the integral of, the 800 plus 150 minus 3x, dx. But you can't incorporate the 20 into that because not every bit of that cable is going to be moved 20 feet. That's not a bad integral to do. I would combine the 800 and 150 to get 950. That whole expression is the weight of the scenario. The dx is the small distance we're moving it, and we're integrating all those small distances from 0 to 20. Which gets me to that. 18,400 foot-pounds. A lot more foot-pounds required than lifting Ryan, or the weight on the first problem. More weight, greater distance. Pregunta, señor.
Are we supposed to assume that the cable is coming all the way off the building, like off the computer, off the building initially? Or would it change the
Yes.
answer if it wasn't?
No, because the theory is once the cable comes around the pulley, it's no longer part of the weight of the problem. So if I started with a 100-foot long cable, all that matters is the 20 feet that's hanging over.
Okay, so it doesn't matter whether you've got 100 feet hanging off or just the 20 feet hanging off? Isn't that more weight that you're moving?
It would only take into account the starting amount.
Okay.
Do you understand what I mean by that? If I have 100 feet of rope, or of cable, and it weighs 150 pounds, then the increments weigh less.
Okay.
So it comes into play in the incremental part of the problem. Does that make sense?
Yeah.
Okay. All right, so let's talk about, these are the most common type of work problems, which is emptying tanks. Now, there's a couple different things that come into play here. Number one is the shape of the tank. We happen to have an inverted cone. That's not a very practical tank shape. More than likely, a problem like this in the real world would involve, oh, I don't know, a pool, which is the shape of a, I don't even know what that is, trapezoidal prism? Like the pool here is weirdly shaped, but I mean, most backyard pools would be cylindrical, no? Like a box? Yeah, with a varying distance there, so it's not as easy. I mean, to keep it simple, we would just fill a kiddie pool in the backyard, right? And we could calculate how much work is required to fill the kiddie pool, right? You don't have a pass to the local park district, you don't have a pool in your backyard, you feel silly running through the hose, so you go to Walmart, buy a kiddie pool for $6, inflate it in the backyard, and lay out there to catch some rays. You with me?
Yeah.
Good. So we can calculate the work to fill it, we can calculate the work to empty it, we can calculate all kinds of different things. What also changes the problem is, what if we're not using water? What if we're filling a pool with honey? I don't know why you would fill a pool with honey, but if, or motor oil, or rocket fuel, or whatever the material is. It's going to require more work to pump thicker stuff. But we'll get to that later. All right, so here's our scenario. We've got an inverted conical tank. The tank is 20 feet deep and a radius of 4 up on top. How much work is done pumping the water over the top edge of the tank until it ends up empty. To calculate the work, you need to know the density of water. Do I need to explain density to you, or do you get it from chemistry and AP chemistry and all your other classes? You know what density is, right? Good. So as the density of an object goes up, in general, the weight of the object goes up. Gold is more dense than water. But here we're just pumping water. You don't need to memorize 62.4 pounds per cubic foot. That would be silly. You'll be given that value for the problem. If the material changes, you'll get a different density. If you're pumping whole milk, for instance, filling a tank to transport milk from the farm, you would have a different density. And there's my picture. Now I chose to define x as the distance down to that little sliver of water. So you see that little cylinder-shaped thing there? I chose to define x as the distance from the top of the tank down to the sliver as X. You could do the problem differently, but roll with it. We're gonna do it this way. So here's what I'm gonna try to do. I'm gonna calculate the amount of work required to take that little sliver of water and pump it over the edge. And then I'm gonna use an integral to add up all the slivers of water. Does that make sense? Okay, so what I need to know first is, what is the weight of that sliver of water? And in order to find the weight, I would do the volume times the density. That gives me that. The volume is actually a little disk, pi r squared dx. You knew that already from our volume unit. And the density is 62.4, because I told you that in the problem. If this confuses you, think about the units. What are the units of volume in this case?
Mass.
Say again?
Volume or density?
What's the volume?
Liters.
No.
Anybody?
Not the numerical value. What are the units on the volume? Anyone? Bueller?
Cubic feet.
Cubic feet. And if you multiply cubic feet by the density, notice the units on the density up there in the top paragraph, the cubic feet are going to cancel and you're left with pounds, which is exactly what we want because we want to weight. Okay, so that's the weight of the sliver. How far am I going to move that sliver? Well, I define the distance that I need to move that sliver as x, because that's what it takes to pump it out of the tank. Which gives me this monster. Okay, so let's break that first one down. Pi r squared dx 62.4 is the weight of the sliver. X is the distance I'm moving it. So that's the weight, which is force, times distance, which is the work to move that sliver out of the top of the tank. And then I added up all the slivers from 0 to 20 because I'm emptying the whole tank. What's wrong with that? Two variables. Which variable are we doing? Are we using as a variable? Dx, right. So dx tells me that x is the variable. And normally in other problems we've looked at, as soon as you see multiple variables, all the other variables become constants. If it's not an x, then it's got to be a constant. So we would interpret, if I just handed that to a math person, they would say, okay, dx is my variable, r squared is considered a constant, so we can move it out in front and do all that other stuff. However, r is not a constant. Notice if I move my sliver up or down, r is going to change. Therefore, r is not a constant, it's a variable, and we have to take that into account. So how do we take that into account? Well, your friend and mine, Mr. Geometry, shows up, and we do some right triangle stuff. Zidler triangles. Gives you that mess. The height of the smaller triangle over the radius of the smaller triangle is equal to the height of the bigger triangle over the radius of the bigger triangle. So I'm talking about this big triangle and this little triangle. That allows me to express the radius in terms of the variable x. That doesn't happen very often. If we were emptying a cylindrical tank, you wouldn't have to deal with it. If we were emptying a box-shaped tank, you wouldn't have to deal with that. It just happens to show up in this weird conical tank. Then I do a little bit of substitution. I get rid of the r's, and I put in a 4 minus 1/5 x. Ooh, and that's a big jump. I was too lazy to do the antiderivative, so I just FN'd it. 33,280 times pi foot-pounds to empty that tank. That's a lot of foot-pounds. Okay, where did I lose you? We're good? We've seen this concept of similar triangles before, haven't we? I forget what it was we were doing then. And it'll come back. There's one other problem on your worksheet that involves the leaky bucket. We're gonna save that till Monday. But let's talk briefly about the leaky bucket for Monday. You should see that as a variable force problem. If I pick up a bucket of water and lift it, that's a constant force problem. The difference with the problem on your worksheet is that the bucket is leaking. So as you raise it, the weight changes. Anytime some element in the problem changes, it all of a sudden becomes a variable force problem, and you have to use calculus. Crazy. Okay? So we'll start Monday by going over the leaky bucket problem together, then we'll talk a little bit about some of the work problems you can do on the homework. That's Monday. Tuesday, we'll review a little bit, test on Wednesday. Last lesson on Thursday and Friday, so therefore we'll wrap stuff up, and then the following week we will get started right away with reviewing for the AP test. Yeehaw! D. Scott.